I want to kick off this deep dive with this image that's just burned into my mind. It's from this old
Mm.
lab footage.
Oh, yeah.
Yeah, they take this tiny speck of metal, I mean, it's barely bigger than the grain of rice, and they drop it into a beaker of pure water.
Right.
And there's no sizzle, no slow burn. It's just boom, an actual explosion, a flash of fire from this tiny thing just touching water.
It is a shocking thing to see the first time.
It just defies everything you think you know.
Huh.
I mean, water puts out fires, right? It's a
Yeah.
coolant. So how does a piece of metal turn it into, well, a bomb?
It's a fantastic question.
Okay, so let's unpack this. We have to figure out the why.
Absolutely. And that why is all about pure sodium metal. It's probably the most dramatic example of just raw elemental chemistry you can find.
It really seems like it.
So our mission today is to get past that initial shock and really understand the high-speed chemical mechanics of it. We're going to break down the split-second steps that turn calm water into, well, fire.
A motive. I like that. Because on the surface, it just seems like total madness. Why is this one metal so, I don't know, angry at water?
It all comes down to where sodium sits on the periodic table. It's one of the alkali metals.
In that first column, group 1.
Exactly. And the defining trait of that whole group is its structure, its electron configuration.
Yep.
If you think back to basic chemistry, all elements want to be stable, you know? They want that full outer shell of electrons, like the noble gases have.
Right, the stable ones?
Well, sodium has 11 electrons, but it only has one single lonely electron in its outermost shell.
Ah, so it's got this extra baggage, this one little electron it's just dying to get rid of to be stable.
You've got it. That's the perfect way to put it. That electron is so loosely held, it takes almost no energy to pull it away.
And water gives it the perfect opportunity.
The perfect opportunity. So when sodium sees water, it's not that it hates it. It sees a chance to finally achieve stability. And the energy that gets released in that process is just enormous.
That makes perfect chemical sense.
Mm-hmm.
But, okay, how does losing one electron translate into an actual explosion? That's the part that's still kind of blowing my mind.
Right. And this is where we go from the motive to the action, the sequence of events.
Okay.
When that pure sodium touches the water, three things happen almost at the same time. They compound on each other.
What's the first one?
Step one is the sodium atom instantly gives up that electron. The water molecule just snatches it.
And that rips the water molecule apart.
It violently strips a hydrogen atom right off the water molecule.
Wow. Okay, so you're fundamentally changing the water itself.
Instantly. And that leads directly to step two, a massive, rapid production of gas.
Hydrogen gas.
Diatomic hydrogen gas, H2. And it's not a slow bubble. It's a sudden, violent rush of flammable gas forming right where the metal is.
So you've got this expanding bubble of rocket fuel, basically.
Exactly. But if it stopped there, it would just fizz. You wouldn't get an explosion.
Yeah.
For that, you need step three, the massive thermal spike. This reaction is what we call highly exothermic. It releases a tremendous amount of heat.
Right.
And not just that, there's a second source of heat. The new sodium ions that are formed, the Na+, they immediately get surrounded by water molecules, creating this thing called a hydration shell. And that process also releases a ton of energy.
So you got two different things making it super hot, all in that one tiny spot.
Concentrated, intense heat.
Ah, okay, I see it now. It's
Right.
the combination.
Yes.
You have the intense heat, which provides the spark, and you have the rapidly expanding hydrogen gas, which provides the fuel.
You've just created the perfect ignition system
So the hydrogen doesn't just bubble away, it instantly bursts into flame because of all that heat.
in milliseconds. The boom you see and hear isn't the metal. It's the hydrogen gas combusting.
It's a tiny, instantaneous fireball,
Exactly right. And the size of that fireball depends entirely on how much sodium you use.
which I imagine brings us to a pretty important point about safety.
A very necessary one, yeah. Watching a tiny pinhead of it react on video is one thing, but if you scale that up even slightly,
The danger just multiplies, doesn't it?
exponentially. Our sources are very clear on this. A piece of sodium the size of a pea, or even just like half a mint leaf, could cause a real dangerous explosion. We're talking shrapnel, serious burns.
So the scientists handling this have to be incredibly careful.
Oh, absolutely. In controlled demos, they often use a piece smaller than a pencil tip, just to be safe. So, and we have to say this is not a home experiment. It is textbook chemistry for a reason.
A vital warning. And, you know, that volatility leads us right into this great paradox.
It really does.
If pure sodium is basically an explosion waiting to happen near water, how can it also be the foundation of something we eat every single day? Table salt.
This is the beautiful central point of chemistry, isn't it? The difference is all about the state of that sodium atom. You have to separate the idea of the neutral elemental metal from the stable ion.
Thus, the sodium in my salt shaker is not the same as that piece of metal in the lab.
Not at all. Remember that electron it was so desperate to get rid of?
Yeah.
Well, in table salt sodium chloride, it has already given that electron away. It gave it to chlorine.
And chlorine desperately wants an electron, right? It's on the other side of the table.
The perfect chemical partner. Sodium gives its electron away, chlorine takes it, and they both become stable ions. Sodium becomes Na plus, chlorine becomes Ki minus.
And they're both happy, chemically speaking.
They're both satisfied. They're held together by a really strong ionic bond. The explosive reactive element is gone. It's been tamed.
It's been neutralized by forming this new stable compound.
A completely stable compound, which is why it doesn't explode in water. It just dissolves harmlessly. The thing that made the metal so dangerous is the very thing that allows it to become so stable and so essential for our bodies.
That is just an incredible transformation.
Yeah.
It's a complete identity shift.
Mhm.
The metal that violently runs from water becomes an ion that is perfectly happy to be in it.
You realize that so much of the world is just a kind of negotiated peace treaty between elements.
So what's the big takeaway for us then, beyond just this one reaction?
I think it fundamentally changes how you look at the elements. It shows you that chemical properties aren't absolute. The pure elemental state of something can be completely different from its state in a compound.
We rely on the stability of compounds every day.
And that stability often masks just how volatile the ingredients are on their own. And going back to the beginning, it gives you a real respect for the energy locked up in these elements. A drop of water makes a metal burst into flame. That's just wild.
It is.
And again, always respect that energy. The sources are unanimous. Don't try this at home. Sodium doesn't joke around.
The crucial point.
Yeah.
And that leaves us with a final provocative thought for you to chew on.
Mm-hmm.
Think about all the other common things we rely on every single day. The plastics we use, the batteries in our phones, the medicines we take. How many of them are only safe for us to use because they're incredibly reactive, incredibly